Hey, so welcome to the Alan Turing Institute Fellows Short Talks, and also welcome to those that are watching online and those that are watching in the future. So the way it will work today is that there'll be 3 speakers and everybody gets 25 minutes to talk and there'll be 5 minutes for questions. And I have the pleasure to announce our first speaker today will be Dr. Natalia Bochkina, and she's from the University of Edinburgh. And her main research interest is understanding theoretical properties of decision-making under uncertainty.
Thank you very much. So, so that's the main, my main research interest. Sort of, I'm a statistician, ranging from theoretical and to applied, or applied to theoretical. And I think it's important to understand that the methods that statisticians, maybe machine learners, use actually do what they're expected to do. So that within statistical terms mean consistency, so they recover the object of interest, but also that they are efficient, that is, they recover the object of interest in the most with the fastest possible, smallest possible error. And I think, one of the future challenges is to incorporate also computational error and perhaps the speed into this framework, which I believe would be an interesting challenge for the Alan Turing Institute. So this is effectively past, present, and future. So my background is both in theory, so I've done some nonparametric regression work, sort of analysis of sparse high-dimensional data, sort of theoretical performance of that, but also some applied work. Particularly, I spent a lot of time both in academia and industry working on analysis of genomic data and some other applications. And here are some of my current research projects. So the first two relate to theoretical properties of Bayesian inference, where we study local concentration of the posterior distribution around the true point. So, Bayesian statistician probably familiar. Most posterior distributions are Gaussian. That's effectively the statement of Bernstein-von Mises theorem for regular models, but what I've studied is what happened for non-regular models, possibly misspecified, and so on. So it's past work, but also some work in progress for ill-posed problems. And the second one is related to that, particularly for the semi-parametric models, where it's similar case, but also there is a nuisance functional parameter. So what happens then? That is joint work with my PhD student Johan van der Molis and Judith Rousseau in Paris, and which is based on our work for more concentration properties of posterior distribution for density estimation, where we've found a way to construct an estimator for possibly unbounded density, totally adaptively to the unknown smoothness, sort of no free parameters, sort of it's all there. Then the next one is sort of a general interest I'm focusing more at the moment is Bayesian inverse problems. So with my PhD student Genova Rodriguez, we started working on inverse problems where the variance is heterogeneous. So usually standard assumption is there is a white noise error. However, in quite a few applications, the noise may actually either be just unknown function, which also evolves either with the signal, dependently function of the observations, or of the true signal, or independent variance. So these are the problems we are working on at the moment, but also I'll talk a bit more about the applied work, which motivates sort of further developments in this area. And the next one, so this is the non-Bayesian, more applied work, is that goes back to builds on my interest in genomic data analysis. So here we look at reconstructing the conditional dependence structure between the genes using gene expression data, but also connecting it to other types of data, and also we starting to work on some theory there as well. So again, this is joint work with my PhD student Jaya Kabaye and Klaus Meyer from Biostatistics, Biomathematics and Statistics, Scotland. And the last one, I think it's just more for the future work, is about how to incorporate perhaps computational efficiency into the statistical efficiency in Bayesian inference, building on some work for misspecified models that I've done. So this is just slide saying that there are lots of challenges in statistical theory at the moment, because classical statistics obviously works for fixed p, but now we have p either sort of large or at least going to infinity with n, perhaps at different rates, and sort of there is no guarantees, which we had at the moment, that the methods just work automatically, right? So there are sort of exciting times to be in statistics at the moment. And often there is some prior information, sort of, however, there are still free parameters. Typical example for me was the lasso approach. It was sort of beautiful idea, right? So you have a high dimensional vector, you know there are some few non-zero values, you just don't know where, and the sort of convex relaxation of the L0 norm to L1, but there is the parameter lambda, right? The, whatever it's called, the how much you weigh the L1 norm polarization. And that was crucial, right? You choose lambda too large, effectively just, you don't have any sparse. You choose it too small, but that way around, you get on very sparse. So it's crucial to choose it correctly, and there was a lot of work until actually it was discovered, both first in theory, I guess, then more applied work, which still showed that it's the right way to estimate. And that was relatively, I guess, judging by the models that I use now, relatively simple problem. So I think it's quite, well, anyway, for me, it's quite exciting. So from what I see, from the statistical perspective, perhaps somebody would correct me, there are two main types of methods to do that. One is penalized likelihood. So if there is a likelihood, one could look at the minus log of it and do the penalization, again, using a prior information. Or there is, in a sense, equivalent way of constructing a Bayesian model using the same prior information, but perhaps with more possibilities for inference, but at a higher computational cost. Right? And of course, there are computational challenges and mathematical challenges. That's I view them as, for instance, one can choose tuning parameters that would guarantee consistency and efficiency, right? So this is just to fix the notation. So y is going to be the data, theta is the non-parameter, and the interest is to recover that theta, perhaps make decisions, construct confidence regions, and so on. And so these are the two main approaches that I see in most papers in this area. One is, I guess, can be F here, sort of minus the log likelihood, and adding the penalty will give a solution, sort of the lasso falls into that sort of setting. And it's usually computationally is relatively simple, because if this is log concave density, if and penalty is chosen to be convex, then this is a convex optimization problem, right? Guaranteed unique solution. So relatively, I think, computationally simple. However, the main problem here usually is to do inference, right? So it's easy to construct a point estimator, but constructing confidence regions or to do inference, for instance, is it zero or not? Is it zero at some of the positions or something like that is much more difficult. In Bayesian model, in a sense, so if you have a likelihood multiplied by the prior, right? So then using Bayes' theorem, effectively you get the posterior. So you can see one-to-one correspondence, right? If you take minus log here, as a function of theta, you get similar expression with the prior being effect or penalty being minus log prior. So in a sense, if you have prior information, you can use either of the approaches, and you can construct point estimators, for instance, maximizing the posterior, that would give the same estimator, but also here we can construct confidence regions and do decision. However, again, in Bayesian inference, one can show, needs to study that the posterior distribution does converge to the right point, at least in some sense, and that the confidence region does represent the right types of uncertainty, right? That it's okay. So what I mentioned before. So there are, of course, computational challenges, and the mathematical is to choose the penalty or the prior so that we have consistency and efficiency. So if there is some sort of distance, for instance, L2 or L1, depending on the problem and time. So the idea is to make sure that there is the theta hat convergence to the true theta and possibly at the fastest possible rate here. And so for Bayesian inference, there, well, as well as for frequentists, so there is a sort of usually one look at the maximum likelihood estimator. That tends to be the paradigm in a regular model, and say, well, it's asymptotically Gaussian, and if not, what is the estimator, right? So usually it's a Bayesian estimator, and in that sense, the Bernstein-von Mises theorem says, well, if we know theoretical sort of behavior of the local posterior distribution, it doesn't matter if you are Bayesian or frequentist, you can still use that sort of asymptotic results to do your inference, right? So it's useful not only for Bayesians, but for frequentists as well. So this is probably my heaviest notation slide. So this is to give you the idea of the standard Bernstein-von Mises theorem. So, and I'll talk about the correctly specified regular models, but also for misspecified regular models. So for correctly specified regular models, we know there is a low information bound, right? So that is the, for the variance of the estimators, that to look at the efficiency. So that's inverse Fisher information. And then for the ID observation, it gives the standard square root and parametric rate. And the Bernstein-von Mises for such model says that, well, the posterior distribution is asymptotically Gaussian, effectively centered at the true value with some bias, and the variance being the inverse Fisher information, right? So effectively it says Bayesian or non-Bayesian, you can just use Bayesian inference and you're okay, even if you're a frequentist. So it's both consistent and efficient. Okay? However, for misspecified regular models, so there is a different information bound. So now we have the true distribution does not belong to the class of the considered parametric models. For instance, one consider normal set of normal models or parametric models, and the density is something different like Cauchy or something like that. And then the low information bound is sort of similar form, but slightly different. So now we have not theta true, but theta star. So it's a parametric model that is closest to the true model, right? So it's a different value. But posterior distribution is asymptotically Gaussian, and it focuses around the same theta star, but with a different variance function. So here, this is the expected value of the square of the derivative of log likelihood, whereas here it's effectively the expected negative expected Hessian. And for the correctly specified models, they are the same, but for here they're different. So in a sense, if you're misspecified, Bayesian inference is not efficient. And that's why, for instance, these results can be used in the approximate computation. So I'm not quoting here, but there was a very interesting paper by Stor and Niall Friel about using these results to change the approximate inference. So I think for composite models. So a composite model is known to be approximation. You just use the first order dependency as long, but you know there is a higher order dependency. So what they do is, because you know the model, you can work out the true variance that, well, the variance that you want to have, and you can work out the actual variance you get into your approximate model, and then you just do a linear correction for bias and variance, and then so effectively you still can construct your confidence intervals, but now you make your approximate inference efficient, and that. So that's for a particular composite model, and I wonder whether that can be used also in a wider set of models. So this is actually a plot to show you what happens for some real data for regular models. So you see the Gaussian contour, the uppermost is 95% credible interval, and it does look fairly Gaussian. However, when model is non-regular, so the case we considered with theta green is when the theta true or theta star from the specified models is on the boundary of the parameter space. So for instance, perhaps a trivial case for correctly specified model is a Poisson likelihood where parameter could be 0, or binomial probability, right? In the binomial likelihood where the probability could be 0 or 1. Or for misspecified models, if you have, say, normal distribution which is truncated, but the truncation is not correct and your true value is outside of the truncation. So it's that sort of setting. And we had it in the practical problem in tomography with a Poisson error. I'll show you in a moment. And so there, what we had is that the rate of convergence is different, so the order n rather than root n. And the asymptotic distribution is no longer normal, but is gamma. Right? And in fact, also the posterior distribution could depend on the parameter which comes from the prior. So this comes from the prior, this comes from the likelihood. And actually, so there is no that term in our case, but there is also another type of non-regular models which has similar asymptotic behavior. It's when the likelihood has jumps which depend on the parameters. So for instance, if your density is supported on theta infinity, for instance, and you don't know theta, so then when you estimate it, your asymptotic distribution will be asymptotically exponential here if your prior is locally constant there, and there is a random shift which depends on data. So that's the type of distributions. Actually, just to run a little bit ahead, we are working in the semi-parametric case with Johan and Judith. So this is the type of density we're estimating. So theta at the lower support point is unknown, and the density itself is unknown. And we are looking at the asymptotic distribution of theta in the presence of the functional parameter. So these are sort of, before I talked about high-dimensional problems, just to say that the results we had apply to the case where p, the number of the variable, is large. Then we have the non-asymptotic upper bound if necessary, so all the effects can be studied. But also now I'm going to talk about the non-parametric problems. So, so these are usually the three types, right? The density estimation, non-parametric regression, and the inverse problems, and where the aim is to estimate the unknown function. So actually the plots I showed you here, so here is the Gaussian, and he just joined sort of Gaussian in this direction and exponential in the other direction. I come from this data example that we worked with Peter. It's a couple of points. I think it's 1 point here, and I think 1 point where in the boundary. So in the middle is the Gaussian distribution, and here it's going to be exponential distribution asymptotically. So that comes from the inverse problem in tomography, where we have a Poisson observation error, well, here, right? So in principle, and the effectively AF is the mean of the Poisson error, so black corresponds to 0. So in principle, we can have Poisson distribution with mean 0, which is fine most of the time, but around the boundary that would complicate the problems. Hence our motivation. But now I'm talking about more general inverse problems with heterogeneous noise that I've been studying recently. So this is the setup. We have indirect observation of function f contaminated by some operator. For instance, in tomography, that would be a radon transform. And we extend the usual assumption that there is a white noise error to the assumption that the variance function can actually be different, or can be either, well, can be unknown or depend on the signal, right, on the AF. And then if we have some prior distribution, for instance, we just put it at the moment in the Gaussian form, then there is one can write, given at least all the parameters, one can write the explicit solution and study confidence interval, but however, there is always the choice of lambda, right? That is quite difficult. So that's what we're investigating at the moment, as well as the convergence rates of the posterior distribution. So we've studied the contraction rates for the non-adaptive estimation when f belongs to the Sobolev spaces, but this is as a preliminary step, and actually we've seen that depending on the type of the error, the rates of contraction can be different from the one which are optimal for the constant variance noise. And at the moment, as I mentioned, we're working on the case where the variance is unknown, also needs to be estimated, or depends on the signal. And the motivation for that comes from, so at the moment working closely with the guys in Glasgow who have observations of the solar flares that come from the sun, and they have different types of uncertainty there, so it's quite exciting even to start modeling it. But also they do have variance, sort of different components in the variance. One is that a constant, another one is actually linear in the signal, and the other one that is quadratic in the signal. So it's it falls into this class of models. And also another setting, so the last one is functional data, so it's not an inverse problems, but they have similar idea that the variance of the sort of, I think it's just voice frequency, depends on the point of time. So they want to estimate the variance as well. And also we have, particularly in solar data and geological structure data, we also have additional, not just time effect, but the spatial effects. At the moment, the inverse problems are solved separately for each point in space, but we're working on doing that simultaneously. And the last problem I'm going to talk about is on the networks in gene expression data. So here is the setting. We say we have two conditions. We'll be considering healthy samples and tumor samples, so with application to cancer, and we have gene expression for each of the samples. And the idea is to reconstruct the correlations effectively between the genes, and more specifically conditional dependence, right? So to understand how genes interact. And the problem we have is where the data is paired. So in a sense, it's sort of simpler in some sense, but more difficult in the other. Because the samples are paired, so the healthy and the tumor tissues are taken from the same patient, right? So for working out the differential gene expression, it's much simpler, but when you have covariance structure, you have this additional term, which dependence between the samples, so it makes things a little bit more complicated. So we're interested in estimating both of the individual networks in each conditions, but also the sort of differential networks, right? So what's the how genes interact differently in healthy and tumor tissues. And so there are several sort of sub-problems there. So we have the testing problem, of course, maybe whether they're equal or not. And if they're equal, if they're not equal, then we do the estimation. So the first one is the sort of graphical lasso method. But then we also have the penalty, which is similar to the one in Danaher and Witten, where they don't have the weights because they have independence. We have the weights which adjust this penalty for the dependence between x and y. So, and also we have a particular choices of choosing lambda 1 and lambda 2, which control the expected false discovery rate. So we have automated choice of that. And so these are the examples of some of the clusters we have. So to simplify, because we have probably about 15,000 genes, and even after reducing the data to those of interest, so down to 7,000, so it's not realistic to reconstruct the whole network. So what we do is we divide it sort of broadly into about, well, I think in this case, 6 clusters. So I'm showing you just the 3. And then we'll look at the different networks in healthy and tumor. So you see the green ones correspond the connections that are specific to tumor, and the red ones that are specific to the healthy individual. And you see the number, there are different types of networks, which actually here correspond to different function of gene. So we can do that. And sort of the last is just a brief slide on what I think can be how these Bernstein-von Mises type results from misspecified models can be used for adjusting the posterior inference. So I mentioned the results of Niall Friel and his student, what they do for the composite likelihoods. So the idea is to use the to perhaps use approximate model for inference, but to adjust them to have the correct inference. Because, for instance, in the classical statistical paradigm, in my view, needs to be changed. Probably agree with quite a few people here that before we assumed, well, it's mostly the sort of random noise error, the observational error, which contributes most to the rates. But at the moment, if the method we propose is optimal, but computationally takes a lot of time, it's not, no one is going to use it. So one might use a simpler method which gives results in a shorter period of time. But I think in theory, statistical theory should take that into account. And in particular, sort of this is one way of doing that. And that's sort of what I was saying, that it would be great to sort of as a challenge to develop a framework for efficient data analysis which takes into account all possible uncertainties, right? So not only statistical, but computational, I guess, privacy related, we'll come to that, and perhaps many others. Thank you very much.
We have 5 minutes for questions. So I was trying to understand a little bit more about the work you're doing with genomics data. So what was the problem right now? Because you said that you have the paired data.
Yes.
Then there was a problem, and I probably because you had to explain it very quickly.
Perhaps
and
I was trying
so
to
I wanted to kind of.
so the problem is so there was only single omega X, omega Y, so you can just reconstruct independently the networks in X and Y and then compare them. It's much easier to do the inference because they are independent, right? So, but as there is dependency, you have additional sort of high-dimensional matrix to estimate in addition to the uncertainty. So one will lose power in a sense. So it's a challenge how to take into account some of the information, but not sort of lose the but still have the good estimation of our original sort of parameters of interest.
I asked one about your last slide.
Sorry.
So I guess looking at the last bullet, I think that actually fits in quite well with the things that I was talking about weeks ago here. So to account for all errors and uncertainties in this process. Can you say a bit more about what kinds of errors you think you're particularly interested in? That could arise because you have sort of, shall we say, raw, messy data.
Yes. Yeah. So I guess there is a variety of errors. So one is so for instance, we assume in the model assumption, right? So for instance, we assume the Gaussian noise. So we estimate the sort of the uncertainty of the observation. So I would call it more statistical uncertainty, right? So suppose the model is correct, all we have is just the variance, right? Sort of that's the uncertainty, perhaps divided by the number of observations, sort of perhaps different in different contexts. Then there is the model uncertainty, right? So if we, for instance, if we assume it's a Gaussian model, but it's not, right? So we can take that into account, or perhaps at least adjust for that when we do the inference to make sure that it is correct. Then I was thinking that the computational uncertainty, so suppose we have the algorithm, right, say the MCMC or something else, but we stop it at some point and there is uncertainty associated like MCMC error or something like that, so perhaps different in different algorithms. So I think these are the 3 types of error I just sort of personally have come across. So as I understand, there is also, say, privacy issue. So if one is looking, say, at the health data or something like that, I think there are people working in, I think, Michael Jordan or Martin Wainwright about perhaps not using all the information, but sort of using part of the information so that one cannot infer who that individual is from the quite vast amount of data. So you only get partial information. I think they study how much information it is, sort of, what is the trade-off? So you still get efficiency, but not loss of privacy. So I think that's another type of error. Perhaps there are more that you know about, or I cannot.
I guess some of the things that I was thinking about are in the messiness of real data. There are anomalous values or there's missing data.
Missing data, I suppose. Yes, that's another one.
Yes. those all probably need to be, if you do have a vision for sort of, general purpose data analysis machine, as it were, then we need to handle those aspects as well.
Yes, I guess I know there is a trend to construct just automated machine inference, but actually I'm not sort of advocating that sort of the automated statistician. I mean, I'm sure it's a great idea, but and I don't. My point at the moment even is just that the theoretical view in statistics does not capture the true situation of the data. So not even it's sort of a step before that just there is a need for even for this theoretical framework, which actually takes into account all uncertainties. Just I guess previously, like 50 years ago, the computational errors was sort of incomparably smaller, but at the moment, but I agree, yes, that there is there are further challenges.
There's just one more question if you want to make it quick.
I was just going to ask about the Turing boundary selection problem.
Yes.
What did you do for the graphical SU type problem that you discussed before?
So, so what we've done is depends on the nature of the algorithm. Just because in the algorithm there is sort of iterative selection, so it's not quite it's not the MCM theta, but it's still iterative type. And so what we do at some point when there is convergence, we use the iterations effectively to estimate the number of false positives the number of effectively zeros and ones in the adjacency matrix, right? So effectively, is there a correlation and is no correlation? And we watch its consistency over the iterations. So that we effectively estimate how many of them are sort of stay throughout that, and so how many are sort of fluctuate. And we use that to estimate the false discovery rate. And effectively, we use that to estimate lambda 1 and lambda 2. I'm happy to maybe talk to you in person to explain how. We have I haven't showed the very last slide. We do have the paper on the archive which explains that.
I want to thank Natalia for coming.